Alright, here we go. Yet another example of shear and moment diagrams, and I'm hoping that after this one, things become even more clear. So, let's see. Draw the shear and bending moment diagrams for the beam and the right. Make sure to label axes appropriately. Alright, so we've got something a little bit more complex compared to the quiz. The first thing you always want to do is do a full body analysis. Meaning you want to find any unknown reaction forces if you have a wall or a pin or a roller. There are no unknowns if a beam is hanging freely at an end. So there's no unknowns here. The only place there are unknowns are at the wall. So at the wall we're going to solve for V, for M, and N, but N is obviously 0 because there's no X force. So the first thing I'm going to do is find my overall distributed load. So I do the area, so 2 kip foot times the length, 6 feet. So that gives me 12 kips at half the distance, so that's going to be at 3 feet. So from there, what I can do is, now that I know what W is, I can do some of the forces in the Y direction and solve for V. V minus W minus 8, and I end up with V equals 20 kips upward. Then I move on to the moment. So here we have moment going clockwise, so negative M, another clockwise rotation, minus W times 3 feet, clockwise, so minus 50, and then another clockwise, minus 8 times 10 feet. So once I do that, I end up with M equals negative 166 kips times feet. Because it's negative, it means that the way that I drew it is not right. So actually, in reality, my moment is going to be 166 counterclockwise. So remember, if you get a negative, it means that the way that you drew it is not correct. Alright, from there, we're going to go on and solve this via the graphical method, because using the mathematical method, equations become very, I wouldn't say too complex, but you have to write 4 equations because you have a jump. So graphical is a lot easier. So let's start with shear analysis. So my entire body, I drew in my 20 kips up and 166 counterclockwise moment that I just solved for at the wall. So we can draw our shear diagram here quite easily. So if we start at point 0, what is our shear force? We have a shear force of 20 kips upwards. So at 0, we know that we start at 20 kips. Then, moving from 0 to 6, we have a distributed load. So in order to find where we're going to end at 6 feet, what we can do is find the area under the curve, or you could think of it as just finding the weight caused by this distributed load. So the area from the distributed load is 2 kips per feet times 6 feet, and remember that it's going downward, so we have negative 12. So what does this tell us? We know that at 0 we start at 20. And we know, because our distributed load is this constant distribution, our shear force is going to be linear. Alright, so we start at 20, and from calculating the area under the distributed load, we have minus 12. That means that at 6, we're going to end up 12 lower than 20. So 20 minus 12, we end up at 8 kips at 6 feet. So let's see here. And like I said, we know that this is linear because our distributed load is a constant load that's distributed. So yes, I hope that's kind of clear. So from there, we proceed to the next section. So we're starting at 20, then we go linearly down to 8. From there, if you think about it logically, we have nothing really, no loads coming in here up until the very end. So that means from 6 to 10, we remain at a constant 8 kips because we have no load being applied up until the very end. And at the very end, at 10 feet, we have 8 kips being applied downward. So because we're at a constant 8, and all of a sudden we get 8 applied downward, then we go and drop down to 0. So that's how we analyze the shear force. I hope that makes a little bit of sense. So from the shear force, we're going to go to moment analysis. The analysis is basically the exact same process. So let's start off with, what is our moment at 0? So if we look at 0, our moment is at 166. But this is the case where our sign convention becomes flipped. So when you're analyzing the moment of the full body, like this, 166 kips here, it is counterclockwise, but in this analysis, counterclockwise means negative. So you just have to remember that and go with it. So we start at negative 166 kip times feet. From there, we know, because our shear force is linear, we know that our moment is going to be parabolic. All we have to do is find our endpoint. And the way we find our endpoint is by finding the area under the curve of shear from 0 to 6. So I split it into a triangle and a rectangle. So 1/2 times 6 feet times the height here, which is 12, plus the height, which is 8 times 6 feet. So I end up with 84 kips times feet. And I know it's parabolic. To find my endpoint, I start from negative 166 and I add that positive area of 84, so I end up at negative 82 kip per feet. Or kip times feet, sorry. Kip times feet. So my starting point is determined by this 166. My endpoint is determined by the starting point plus the area under the shear curve. Alright, from there, so we're at this negative 82. What do we do next? So we're at negative 82, but what we have all of a sudden is this 50 kip times feet moment. So that means that we have a jump. We're at negative 82 and we need to jump 50. But 50 here is clockwise, and remember, when you're analyzing the full body and doing this graphical method, clockwise is actually positive. So what we do is from negative 82 we jump up 50, and we end up at negative 32 kip times feet. I don't know why I did divided by feet, just ignore that, it should be times feet. From there on, all we have to do is, we know that at 6 we're at negative 32. What is our endpoint? So we just take the area under the shear curve from 6 to 10. So the area is going to be 8 times 4 feet. That gives us 32 feet. So we know that our endpoint is going to be negative 32 plus 32. So we end up at 0. And we know here that the curve for the moment is going to be linear because the curve for shear is constant. So this goes back to calculus 1 and calculus 2. When you if you start with a parabolic curve and you take the derivative, you get linear. When you take the derivative of linear, you get to constant. And then when you integrate constant, you go to linear. When you integrate linear, you go to parabolic. So that's kind of, it's going back to the calculus and differential relationships. Alright, so the most important thing is to understand what is your start point, what is your end point, and using the area to determine if you're parabolic, if you're linear, or if you're constant. And then whenever you have a shear or a moment at a certain point, it becomes a jump. So we had to jump here because we had this 50 kip times force moment. Alright, the most important thing that a lot of you are getting confused is the sign convention. So whenever we're doing the mathematical method, whenever we have to write an equation for shear and moment and use that to graph, so that's when we cut the beam and we have to solve for shear and moment. It's important that whenever you cut the beam and you look at everything to the left of that cut, that your shear is pointing downward and that your moment is pointing counterclockwise. So in here, the sign convention is normal, like we're always used to. When writing the equation, clockwise is negative and counterclockwise is positive. What flips the sign convention is when we go to the graphical method. When we're analyzing the entire beam, just like we did in this problem, and you're thinking to yourself, why is this counterclockwise 166 actually negative and why is this positive? So here is when the sign convention becomes flipped. When we're looking at the whole beam and putting it on the graph, counterclockwise is negative, clockwise is positive. And it makes sense because if I were to cut the beam here, this, and then write my equation for moment, this comes out as positive. And you don't have to work through it, you just need to understand when to use each sign convention.